Ladies and gentlemen, welcome to video lecture number 9 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in late 2017. We are now October 10th in the year 2018, about a year later, and in video 9 we now are at the end of part 2 of the Fivefold Suns section 2, 3.2. In section 3.2 we will discuss briefly the physics of the suggested icosahedral arrangement that was proposed in video 8 as a model for a spheroid like the Sun. And finally, we will state the geometrical parameters of this suggested arrangement, which will have to be matched against the actual phenomenology of the Sun and the geometry of this phenomenology, so as to see if the model fits in any way with the actual solar ball. As you see, we are at the end of section 2.3. We already described the proposed geometrical arrangement in video 8. Now we go further into its discussion. We briefly first discuss the physical properties of this arrangement. It is the equivalent of the solution of the Thomson charge problem for 12 charges at the surface of a sphere. Then we will show an experiment which represents somewhat of an intermediary between the physical problem and the purely geometrical problem as solved in video 8. And this will be an experiment with magnetized spheres. Finally, we go to the comparison to be performed with large-scale features of the solar ball. The Thomson problem was stated by Thomson in 1904. This is the man who discovered the electron, and he wanted to know how certain numbers of electrons would be optimally distributed at the surface of a spherical shell. In modern terms, it is stated as follows: how n-point charges at the surface of a sphere are distributed to minimize potential energy. The solution is to place the charges, all of which share the same sign for their charge, at the vertices of a regular icosahedron. So it is exactly the same solution as the purely geometrical problem called the Thomas problem, which we already also called in video 7 the optimal spherical code problem, and is also called the sphere kissing problem. The solution is the set of 12 vertices of an icosahedron. We now show an intermediary problem, intermediary between the purely geometrical problem and the physical problem with electrical charges. And it is an experiment with 12 magnetized spherical balls that will show how this problem works. We have a set of 12 metal balls. They are spherical with equal radius. Each one is independent, but a strong magnet was applied at this end of this line of spheres, so that they are now magnetized in the same direction, and thus they hold together. You see, they really hold together. Now, if we apply pressure to this set of 12 spheres, this is the compound that spontaneously forms if any stable shape is achieved. You see there is a polar ball at the top, a polar ball at the bottom, and there are two sets of 5 balls, 2 rings. This is exactly the same as in the case of the of the 12 balls inside a glass envelope that was shown in video 8 and proposed as the icosahedral model that we suggest. Now, if we apply pressure to these 12 spheres, as I said, if a stable arrangement is reached, it will be the arrangement that was shown. But if we are not lucky, we will not reach a stable arrangement, like I apply pressure but I fail to apply isotropic pressure. This is what we get. So we have to use an additional 13th ball to use as a cavity, as a core, and then if we apply pressure in a clumsy way around this core, nevertheless, by trial and error, in the end we will arrive at the fivefold arrangement that was shown first in this video. The central ball has to have a certain diameter, which is a diameter that was already stated in video 8, and this is how we reach a stable assembly of the 12 outer spheres. We now turn to the geometrical parameters of such an arrangement that we will have to check against solar phenomenology. We now are ready to make a list of the salient features of the proposed icosahedral arrangement, the relevant parameters and the geometry of this arrangement that we will want then to check with comparison to the solar ball and its actual phenomenology. These relevant parameters are two radial fractions that were already stated in video 8, and in the current video 9 we will then state the 6 icosahedral angles of interest in this arrangement. The radial fractions, as we saw in video 8, they are the dimensions of a central cavity and of a outer envelope beyond this cavity, intermediate between the overall sphere under investigation and this internal core. As for the central cavity or central core, the radius of an icosahedral spheroid would be, for its cavity, 0.3108, etc. radius fractions. In the case of the solar ball, it would be located at 0.310, etc. Radius fraction of the photospheric solar radius. In the case of an intermediary envelope, which would run through the vertices of a basic icosahedron, and as we saw in video number 8, the radius of this envelope would be located at 0.655, etc. radius fraction. Again, if this was the case in the interior of the Sun as a fraction of the photospheric solar radius. We now turn to the 6 salient angles in icosahedral geometry that we should find in such an arrangement, and they are as shown in this table. There are 6 major angles plus the right angle of 90 degrees and an angle of 37.37 degrees. We see that the major angle that is first to be stated is the so-called icosahedral central angle. It is found at the fivefold vertex of this solid. In the model that is shown here, the angle appears between any two red sticks which delineate the line between the center of the icosahedron and one of its vertex. Any two, of course, of the neighboring such red sticks. You see, for instance, here, this red stick and this red stick, they are at an angle of, at a central angle of 63 degrees. And this is also, by the same definition, the angle between this white dot, which is a vertex, and any other of the neighboring white dots, and the neighboring vertices of this icosahedron. This angle is very well known in scientific literature. This is less often stated, but is sometimes stated in scientific literature, 26.5 degrees, and it is the angle between a vertex of the icosahedron in the toroidal region and the equator of this solid. If I now show an equatorial line for this icosahedron, you see any of the white dots that represent vertices in the toroidal region. In the upper set of 5 vertices in a northern hemispheric ring, they are at a central angle of 26.5 degrees versus the equatorial line. And this is the same for the 5 white dots, which are the vertices in the lower hemisphere, let's say a southern hemisphere. So if you now look at the table, you will see that 63 plus this figure, they add up to exactly 90 degrees. And if we look in the other side of the table, these two values also will add up to 90. Then there is in the lower part a set of angles that add up or subtract, in this case, to a value of 37.37 degrees. We are not going to comment right now on all of these angles. Maybe we should nevertheless state the face center versus equator angle, which is 10.8 degrees. You see, if I draw the equatorial line, a face center will be located somewhere here, and it will be at a distance of 10.8 degrees. These angles may seem complicated, but the underlying trigonometrical formulae are straightforward. You see, for the central angle, its tangent is 2. For this angle, its cotangent is -2. For this angle, we have a tangent of minus the mean and extreme ratio of 1.618. And this one has for its tangent the inverse of this ratio. The inverse of 1.618 is 0.618. So now we are finished with video 9. We have this list of the salient geometrical features of the arrangement of fivefold symmetry that we suggest for a spheroid like the Sun, and we are ready to compare this set with actual solar phenomenology. Thank you for your attention.